Everyone, welcome to Black Hat. This is Zeker Chu. He's going to be talking about the checking array-bound violation using segmentation hardware.
Okay, thanks. So in this talk, I'm going to talk about a sort of like a somewhat technical way of checking array-bound violation. So the basic idea is to try to use this program transformation approach so that we can compile a program in such a way that the resulting binary is guaranteed to be free from buffer overflow vulnerabilities. And its runtime performance overhead is relatively low compared to existing approach. So if you look at the landscape in terms of the attack primitives that modern worms use, they actually fall into two categories. The first category is sort of automatic approach. Like, you don't have any, you don't have to do anything. Right? As a user, you don't have to do anything. You just have some vulnerable program running on some servers. And the attackers are able to exploit this vulnerability and try to get in, control your application and even the underlying machines. What they can do is they can inject some code into these applications, or they can actually use the existing code already in the application that's known as return to libc attack, or they can actually just change some of the data in the application in such a way they can subtly change the program flow or even the arguments to the system calls. The second category requires user input, like somebody sends a malicious attachment in the emails, and so user actually have to click on it, or send in something, embedded something in the web download HTML pages, or even just like files being transferred between FTP sites and P2P softwares. So today we are going to look at mainly these automatic attacks, because for modern worms, that's what we are worried about. Like, you just have software vulnerability and somebody can exploit it to try to propagate worms from one machine to the other. So these automatic attacks typically are referred to as control hijacking attacks, because they try to hijack the control of the victim applications and sometimes even the underlying machines, turn them into a zombie or something. And interestingly enough, these control hijacking attacks typically have a well-defined three-step recipe. It's actually very, very clearly defined how they actually do these kind of things. So the first thing they try to do is they try to insert some sort of malicious stuff into the address space of the victim application. So you have victim applications running on the machines. Somehow, the attacker, by inputting something, you can tamper with the address space of the application. So this is just like a real, airplane hijacking. You try to sneak some weapons into an airplane. And the second step the attacker tries to do is that once he can inject something into the address space, then you try to trick the victim application to transfer control to some place, either to the injected code or to some existing code. So it's like a hijacker trying to take control of the victim's airplane. And once the attacker grabs control of the victim application, now he can do whatever he wants by issuing some sort of damaging system call to achieve whatever purpose that he has in mind. So the question here is that how does the attacker actually override or tamper with the victim application's address space? So the most dominant way that people use today is buffer overflowing. They try to input something and then overflow the particular storage space allocated to receive the input packet. And the other possibilities include integer overflowing. This exploits the finite precision computer arithmetic underflow overflow. Or the attacker can prepare malicious format streams used in printf-like functions, so they can read stuff or write stuff into the address space. And the kind of target they use to overwrite, including things like stack, heap, or global area. So these are all pretty well understood stuff. So just to give you an example to illustrate this three-step procedure, so this is a simple example that I made up. So basically, we have a program that consists of two functions, main and input. In the input, it allocates a local integer array called user ID, which has 5 integers. And in this particular program, in this particular function input, when you try to input something from the outside, it doesn't check the array bound, and that's where the mistake is. So as a result, the attacker could actually overflow this particular array, user ID, and try to override something behind this array. And typically, what they try to override is something called control-sensitive data structure, like return address, function pointer, GOT, and so on. In this case, it's a return address. And the value they use to override it is some places they inject the code. In this case, position 100. So that's what happens. So you can say the first step they try to do is they try to overflow. And that's the very first step. So they can overflow behind this allocated storage space. And then they try to steer the control of the application by overwriting the control-sensitive data structure with something that they inject. And then eventually, once they grab control, they can make system calls, whatever system call they want, in particular, forking a share, sending a file, and so on. So given this analysis of the three-step procedure being used in these control hijacking attacks, we can actually develop a corresponding multi-pronged defense strategy. So if we want to stop this kind of control hijacking attacks, and again, these control hijacking attacks are the primitives used in modern worms, we can actually do sort of one of the three things. So the first thing is that we can stop these control hijacking attacks by preventing overflowing in the first place. We just don't want anybody to overflow and tamper with victim applications address space. And that's array-bound checking, which is the topic of today's talk. Or you can stop control hijacking attacks by saying that I'm going to prevent any illegitimate control transfer. Right? Remember, the idea there is that the attacker can actually override some sensitive data structure like return address or function pointer and steer the control of the application to wherever the attacker wants it to go. So if we can somehow stop that, then still the attacker will not have a chance. And this is another project called Food that actually try to check the target address of every indirect branches that include return, include indirect jump, and including indirect call. So every such instruction, their target address will get checked and to make sure that they don't go to bad places. So that's the idea of the full project. Or you can say that this guy is really good, then somehow he can overflow something and steal the control of the application, and then start to making system call. And you can also stop this control hijacking attacks by saying, I'm going to prevent all the illegitimate system call. So you have to have a notion of what system calls are legitimate and what system calls are not. So there's actually a project called PAID that does exactly that. From a particular application, we are able to come up with the legitimate system call pattern, and at the runtime we check it, whether it's actually legitimate or not. And so this is the talk that I gave last year. So basically, any one of these three lines of defenses will do, okay, depending on the user requirements or system configuration. But today we are going to look at only array-bound checking, all right? So the basic idea is that we don't want people to overflow. We don't want people to tamper with my address space. So we want to prevent all unauthorized modification of the address space. So this should be the cleanest solution, right? There are a lot of solutions to the software security problem. They try to do really weird things. Once they come in, we check this, we check that. I claim that the cleanest solution is to stop them from overflowing in the first place. They should not come in and tamper with your address space in any way they want. So that's what I think is the best way to solve this problem. So the basic idea of array-bound checking is to say that for every memory reference in the program, I'm going to check whether this particular reference lies within the upper and lower limit of the corresponding object. Right, that's the basic idea. So for every memory reference, if it belongs to an array, I can find out what's its lower bound and upper bound and make sure that no reference can exceed it. This includes both arrays as well as buffers. So it includes also things allocated from malloc, for example. So there are actually just two issues that you need to deal with to do something like this. For every memory reference, first you have to figure out what is its corresponding object, higher level object like array, structure, and buffer, and so on. And then you can perform the corresponding limit check. Like, does this particular reference exceeding the upper and lower limit, and so on? So this is like a pretty simple idea. Of course, that's what you should have done in order to prevent people from tampering with your address space. So if array-bound checking is such a great idea, how come it was never adopted as a mainstream solution to this buffer overflow problem? Right? It's sort of obvious, and then seems like there's a well-known algorithm to do this. And the answer is because existing software-based array-bound checking compiler is just simply too slow. Okay, so the performance penalty reported in the literature ranges from 2 to 30 times slowdown. So the main issue that this particular talk tries to address is that how to reduce or even eliminate this runtime penalty by exploiting certain architectural feature in x86 architecture. So before we go into the idea, I just want to review the virtual memory hardware architecture in x86 architecture. So every memory reference in x86 architecture includes two components. One is a segment selector, the other is offset, okay? So whenever you write a C program, for example, eventually get compiled into binary, every memory reference consists of these two things. You have to specify the segment selector and you have to specify the offset. And with that segment selector, it's going to go to either a global descriptor table, GDT, or local descriptor table, and find out the corresponding segments base. And with that base, it's going to add it to the offset to form a so-called linear address. And from that linear address, you can go through this so-called two-level page table to arrive at the corresponding physical address, which is the address that you use to access main memory. So in this process, it actually does one more thing, which is called segment limit check. So just to make it simpler, so basically we have a virtual address which consists of segment selector plus offset. And in the process of forming linear address, the hardware already performed such a check. They make sure that the resulting linear address lies within the lower and upper limit of the corresponding segment. And virtual memory hardware of x86 architecture has been doing this for years. It's just that for most operating systems, they simply ignore segments. So this particular hardware feature never gets used. So it's not like an additional hardware support or anything. Every memory reference in every x86 box is doing that. It's just that nobody tried to use it to their advantage to do something. And that's exactly what we are trying to do. So the basic goal of this cache system is trying to exploit this segment limit check hardware to perform array bound checking for free, right? So you see the similarity between the two, right? For array bound checking, we say for every memory reference, I'm going to find a corresponding object and figure out whether this particular memory reference lies within a lower and upper limit of that object. For segment, it does similar thing, right? For every reference, it also checks whether it lies within the lower and upper limit of that corresponding segment. So that's exactly what you want. So all we have to do is just to allocate a segment for each array or buffer in the program, and then generate code accordingly, such that the resulting segment limit check hardware is doing this array bound checking for us essentially. Right? So that's the trick, to twist it to do it, and therefore you don't really need special hardware support, and you can speed up the array bound checking dramatically. So there are a couple of design issues associated with cache. So the first issue is that given a memory reference, how do you map or find the corresponding high-level object that includes that particular memory reference? And the second thing is how do you generate code such that you can twist the segment limit check hardware to do what it is supposed to do, implicitly performing array bound checking. And then in some cases, you just cannot use this segment limit check to perform array bound check. So you actually have to fall back to software array bound check. So in those cases, we have to generate code such that everything gets checked. But then there are other sort of architectural limitations of x86 architecture that sort of prevent this idea from happening easily. For example, there are only a finite number of segment descriptors in x86 architecture specification. And there's a very small number of segment registers that keeps us from using multiple segments simultaneously. And also there's this issue of once you want to allocate a segment for each array or object, you have to modify this local descriptor table, LDT, very frequently. And LDT typically is living in the kernel space. And therefore, it means that you have to make a lot of system code just to modify it. And that turns out to be a big issue for us. So for the first problem, like how do you associate a particular memory reference with its corresponding high-level memory object? One approach is to organize all the memory objects in the program as a spread tree. It's just like a trie, essentially. So you can actually find, given a memory address, think of it just like a tree. You can give a memory address, you can actually look it up in the tree and to search the corresponding object. And there you will include the corresponding lower and upper bound. So in this particular approach, that means for every memory reference, I need a spread tree lookup. Like a memory access is very simple, read and write, a single instruction. But for that, I need to do a spread tree lookup. So that's like pretty expensive. But the good thing about this approach is it's compatible. It's compatible with the legacy libraries or legacy codes. And this approach has been used in Imperial College's bounds checking compiler, right? So as I said, the advantage is compatible with the legacy code. That's pretty nice. It's actually very important. And the disadvantage is very slow. So sometimes it could be up to 30 times slower, okay, because of this additional lookup for every memory access instruction. So that's kind of bad. An alternative approach to the spread tree implementation is to use a shadow variable, or so-called fat pointer. It's just a matter of whether you maintain a satellite data structure for every pointer variable, and then whether they are consecutively located together with the pointer, or they are stored someplace else. So whenever you want to access something, instead of looking up in a spread tree, the corresponding satellite data structure contains all the information you want, and then you can do your check accordingly. So that's pretty easy. So the advantage of this approach is fast, but the disadvantage is there's a compatibility issue. Like you can imagine that for every pointer, there's actually a satellite data structure, and when you actually have to pass a pointer, you have to pass the corresponding satellite data structure. So the API interface will not be compatible anymore, right? So you have to pass in additional stuff. So there's a compatibility issue here. And also, the idea of shared variable and fat pointer is somewhat cumbersome for some data structure. Right? If you have some pointer, it's probably easy. But what if you have pointers within a structure, and so on? So where are you going to put this shadow satellite data structure, and so on? So there are issues like that that makes this particular approach not as clean as a spread tree implementation. All right. So just as an example to show that and how this is done. So for example, you have an original pointer P on the left column. So you have to augment this particular pointer with additional data structure to recall additional stuff. In this case, you have to recall the corresponding segment. Remember, we allocate a segment for every object, right? So I have to recall the corresponding object's segment. There's LODTI, the index into the LODT. And then we have to recall the corresponding base and limit. This is useful for software array bound check as a fallback mechanism. And for array, we have to allocate additional satellite data structure like this. And then whenever you do arithmetic operation with a pointer, now not only you have to assign pointer, you also have to assign the corresponding fields in the satellite data structure, right? So in this case, you assign A to P, the right-hand side, then you have to manipulate their corresponding satellite data structures accordingly. All right? So that's what you need to do. Like once you create this additional data structure to keep track of which pointer belongs to which object, that's the additional stuff that you have to generate. So Cache actually uses a hybrid approach. We actually try to maintain the compatibility as much as possible. So in general, it's a spread tree. But we know that spread tree is very slow, right? Because for every memory reference, you actually have to look up that spread tree. So we try to take advantage of the fact that for many memory references, they are so-called named references. Like, you don't need to dereference a pointer. In those cases, we are going to use a shadow variable. And only for pointer references, we use spread tree, okay? So that's the key idea. And moreover, we are trying to, the way that we maintain these shadow variables are sort of somewhat unique compared to previous approach in the sense that we try to maintain compatibility. So instead of passing the shadow variables of these pointers across function boundaries through the stack, we actually pass them through the heap by maintaining a shadow stack. So this guarantees that even when our program call a legacy program or a legacy program call us, your works, right? There's no problem there. So we actually guaranteed backward compatibility that way. So as an example, for example, you have this function called chain, F1 call F2, F2 calls F3, F3 calls F4, and so on. So F2 is a legacy function, okay? And F1, F3, F4 are new ones that we compile, right? So F1 can pass something into F2. So in this case, F1 calls F2, so it has to pass in A1, A2, A3. And we also pass the corresponding shadow construct like A1.S, A2.S, and A3 doesn't need it because it's not a pointer, and so on. And for when F3 calls F4, again, F3 will pass A7.S, A8.S. These are the corresponding satellite data structures, all right? Now, in this particular case, because F2 is a legacy function, it really doesn't check this shadow stack. So even though F1 passes something to F2, those things that get passed essentially get ignored by F2. But when F2 call F3, F2 doesn't send anything to F3. So when we compile F3, we know that sometimes we might get called by a legacy function. So we'll check the shadow stack. And since F2 doesn't send anything to F3, we say, oh, I probably get called by a legacy function, so I don't really have any shadow data structure to work with, and so on. But that's fine. But between F3 and F4, they are all compiled by cache, so they have the corresponding shadow structure, and they can work correctly. Right? So that's the idea. So given that we already can set up sort of the code correctly so that we can check we can map a particular memory reference to the corresponding object. So now how do we generate code? So this gives you a simple example. So the source code statement is AI equal to 10. Right? I have an array. I just pick up the ith element of that array A and assign the value 10 to it. That's the source code statement. Without array bound checking, that's the 4 instruction that you need. You are going to load that index I, and then you multiply it by 4, so that they give you a 4-byte entry. And then you load the base address, and then now you're going to assign that value 10 to the corresponding memory location. So that's it, pretty simple. Now, if you add array bound checking code, that's what you get. You do the same thing, load I, and then multiply that I by 4, and then load the base address. Now, you have to load the corresponding shadow structure pointer as well, all right? And you have to, now that you allocate a segment for that particular A, you cannot use the same segment anymore. So each array or each object or each buffer has its own segment. So we are going to load the corresponding segment into the segment register. And then we are going to compute the offset, and then we are going to assign, doing the assignment. So the red ones are the ones that we have to add additionally, all right? And it turns out that if this code is actually executed within a loop, those 3 instructions, the red ones, need to be inserted for every memory reference. But those 3 instructions are actually loop independent. So you don't really even need to do anything. You just generate these instructions inside a loop body, and when you turn on the compiler optimization, these 3 instructions will get lifted out of the loop body. So essentially, what you do is that in the loop body, you still have 4 instructions, not 7 instructions. The 3 instructions that we add actually get lifted out of the loop automatically without us doing anything. So essentially what this means is that in order to use this cache idea, there's actually no additional overhead for every array reference. But there's some preparation overhead in the beginning of the loop. These are these 3 instructions I'm talking about, right? So that's the beauty of it. Like previously, we say that every time, if you want to implement array bound checking, you have to spend additional time to look up, to associate a particular memory reference with its corresponding object, and then you have to perform the lower and upper bound limit. Right there, you probably need 6 instructions just to do lower and upper bound check. But here, every memory reference, array reference, doesn't require any additional overhead. So that's the beauty of cache. Now, one of the problems with the cache approach is that x86 architecture only provides a very small number of segment registers. Right? It only provides 6 of them, and 3 of them are already taken: the code segment, data segment, and stack segment. Okay, so we are only left with 3 segment registers. On top of that, some string manipulation instruction actually use one of the segment register, ES. So in order for us to use 3, we actually have to modify some of the string manipulation function in glibc so that they can use some other segments. So, and we can actually try to use the 4th segment register like SS if we can replace all the push and pop instructions with just move instructions. We can also do that, but we didn't actually do that. So in the end, we only have 3 segment registers to work with. That means that at any point in time, I can only have 3 objects, buffer or array, 3 buffer or array in the processor simultaneously. If within a loop, that loop actually uses more than 3 arrays or buffers, then I have a problem. Okay? And this is where software array bound checking comes in. If you have a loop, or especially nested loop, that uses more than 3 buffers or objects, then all the other array references behind the first 3 need to be checked in software. Okay? And that's why we need this additional fallback mechanism using software array bound checking. Okay, so that's one problem with the the very small number of segment registers. So this is sort of a concern that we have in the beginning of the project. We don't really know better. We have to really implement it and then try it on real program to see whether this is a problem or not. In the end, it could be that a lot of the array bound checks actually need to be done in software. So it defeats the whole purpose of cache, which try to exploit the segment limit check hardware. And the other issue is the segment descriptor management. In x86 architecture, it only has 8192 segment descriptors, AK essentially, right? So it's not particularly large, but it's not small either, all right? But we don't really know whether this is a nonce or not. And remember, I want to allocate a segment for every buffer and array in the program, including local array. Every time you call a function, that function includes a local array. That local array also needs a segment. All right, so potentially we could need a lot of segments. Or if I have a recursive call, and that recursive call has a really long depth, and that recursive function actually includes a local function, then I could have a problem. So whenever I do this for local array, I can allocate a segment for a local array statically, so because it's declared. And for global array, I can allocate a segment for it statically, and for local array, I have to allocate it dynamically. So whenever I enter a function, I see there's a local array, then I need to grab a segment from the segment pool. And the same thing with dynamic array, like malloc and free. So I would allocate when malloc and deallocate when free. So as I say, there are only 8192 segments. 2 of them are already used by us. One is used to implement a special call case called cache modifier LDT. I'll talk about it in a minute. And the other is a fallback thing. So this particular segment whose segment limit is set to 4 gigabytes. That's the entire address space. That essentially says that you don't do any check, right? Because there's no upper and lower bound. It covers the entire address space. Of course, any check is a no up operation. So this is meant for fallback. So again, I'll talk about it in a minute. So really, we only have 8190 segments, and some of the segments actually get used by Linux as well. So in a sense, we probably have something like 8180 segments to work with. And the question is it good enough for real network applications that are potentially vulnerable to buffer overflow attacks? Again, we don't know in the beginning of the project, so we have to try and see what happens. So one of the major issues that we run into in this project is this LDT modification overhead. So the problem is the following. Remember, for local array, if you have a function that allocate a local array, and I say that for every array, I need to allocate a segment for it. But in order to allocate a segment, I need to fill in the corresponding segments as segment descriptor table entry, LDT entry, right? But LDT lives in the kernel space. So that means that for every function call, I need to make at least 1 or 2 system calls just to manipulate these LDT entries. And that's not very nice, right? I mean, I don't really want to turn every function call into a system call. That's pretty expensive. So one way to solve this problem is that what if we lift this LDT from kernel space to user space, right? So then we can manipulate LDT at the user space. And so the original assumption is that since nobody is really using segments anyway, like most of the application, most operating systems simply just assume a couple of segments and that's it. They leave the LDT alone. They never actually touch them anymore. So there's actually nothing sensitive in a LDT. In theory, that's correct. Unfortunately, in x86 architecture, it also allows people to set up something called call gate. And the call gate is a special segment that allows, that can point to any code. And that call gate allows users to run any code that it points to at the kernel level. So that means that if I get to manipulate LDT at the user space, I can set up call gate. Then I can run a piece of code at the kernel level if I want to. And that's obviously not a good idea. So that means the idea of lifting LDT from kernel space to user space is no good. It's just not acceptable from a security point of view. So then we said, okay, maybe I can try to make the system call as fast as possible. So if you just call in Linux, it actually provides a generic system call for you to modify LDT entry. Like in this case, it takes probably something like 781 clock cycles. So we try to reduce it, do whatever we can, reduce unnecessary check and so on, and using call gate to set up this system call, it reduces the number to 253 clock cycles, still pretty high. So turns out that sort of like this is kind of important, so we actually have to do something else. So that something else is about caching. So the general scenario that we observe is that in a lot of these sample programs that we tested, sometimes you actually deallocate something and then reallocate again, and deallocate something and reallocate again. So an example would be something like this. So let's say you have a function main, and that has a loop. In that loop, you call another function foo. And within that foo, it actually needs a local array. So within a loop, you repeatedly call foo. And every time you call foo, you actually have to allocate an entry from LDT. And every time you return from foo, you have to deallocate it. But the good news is that this pattern is repeatable. So instead of repeatedly allocating and deallocating by manipulating the LDT entries directly, we keep a user-level cache to say that if the next request whose base and limit is the same as the previous one that I deallocate, then I don't have to touch the kernel, because I don't really need to rewrite the kernel, the LDT, the segment descriptor table. It's the same, right? So this idea actually reduces a lot of the overhead related to LDT modification. And it turns out that it's particularly effective for these local arrays called within a function or called within a loop. So that's the example. And it turns out it's actually this is the main reason why the whole thing can work. Like if you have to pick an idea other than the general idea of allocating a segment for every array and buffer, this is the main key. That without this, it would be very bad. Right? For local array, you have to make even a lightweight system call is just too much. And then there's some kind of other issues that's somewhat exotic related to x86 architecture. So in x86 architecture, if you have a segment that's less than 1 megabyte, then remember there's a segment limit, right? So the question is that the segment limit is in terms of what, right? So usually it has a particular bit called granularity bit in the corresponding segment descriptor table entry. That when a granularity bit is off, that means that when you specify limit, it's in terms of bytes. All right? But when the granularity bit is on, it means it specifies limit in terms of megabyte. Right? So this allows you to grow the segment beyond 1 megabyte, essentially. That's the idea. So if you look at, we have an array that is more than 1 megabyte. That means that we have to turn on the granularity bit, right? Because I need a segment that's larger than 1 megabyte. So in order to do that, I have to turn on the granularity bit. So that means that I might have some problem in terms of doing exact array bound checking. So this example shows you that. So imagine that I have an array that's expressed by the interval between these two red lines, okay? But in order to do this, I actually have to specify this in terms, actually, I'm sorry. So when the granularity bit is on, the unit is actually 4K byte, not 1 megabyte. It's actually 4K byte. So that means that whenever I allocate a segment for this particular array, which is larger than 1 megabyte, I have to allocate the smallest integral multiple of 4K kilobytes behind this particular array, right? And that's what happened. That's what that yellow line represents. So if I actually do array bound checking, I'm actually checking the lower bound and upper bound of the segment, which is not the same as the lower bound and upper bound of the array. Got it? Right? Because I'm forced to allocate a little bit more than what I actually need when the array is greater than 1 megabyte. That's just the peculiarity in x86 architecture. So when I do this, that means that when I'm checking things, I'm not exactly checking the array bounds, right? I'm checking the segment bounds. These two things are not the same. But it's actually okay, not too bad. So what we do is we align the upper bound of the array with the upper bounds of the segment, because most of the array bound violation is related to upper bound. But there's still something that's related to lower bound, especially with respect to integer overflow. So what we do is that whatever in between the lower bound of the array and the lower bound of the segment, we should not allocate anything, right? So that means, okay, you can underflow the array, but you cannot underflow the segment. But between the lower bound of array and lower bound of segment, there's nothing important that you can overflow. So you can overflow, but there's nothing there. So that's probably not too bad. So that's what we end up doing to solve this particular problem. So now, with all these machineries in place, that we actually implement a full-scale bounce checking compiler based on GCC. And actually based on a particular version of GCC that already performs a limited form of bounce checking called BCC. Okay, and this runs on this particular platform and so on. So if we take a step back and try to figure out what exactly we are trying to do. So remember the idea is that I'm going to twist the segment limit check in x86 architecture's virtual memory hardware to perform array bound checking for free. That's the main idea. So we are claiming that for every memory reference, you don't really need to do anything. The hardware is already doing the stuff for you. That's the claim. But in order to make that happen, we have to set things up, all right? And that incurs additional overhead. And it turns out there are 3 types of overhead. One is per program overhead. Like you are given a program, in the initialization phase, I have to set up this free list for LDT, cache, and so on, as well as allocate entries for global arrays and so on. And then there's per array overhead. This is in particular with respect to local array within a function. Every time you call a function, right, remember I need to actually make some call in order to modify the corresponding LDT entry, right, to add the entry into the LDT, and when the function exits, I have to deallocate it, and so on. That's per array. And there is something called per array use. So for example, within a function, you might declare a local array, but that array gets used in 2 loops, right? So this per array use overhead captures that every time an array is used, what's the additional overhead you need, right? So an array could be used in multiple loops, and that's for each such use, it is going to incur some overhead. So it turns out that the most important part is really this per array overhead thing. Per array use is nothing. This is related to how you load the segment register and compute the offset and so on. And per array overhead is the one that we try to modify, right? We say lifting the whole thing to user space, no good, and trying to have a streamlined, optimized, modified LDT system call. It gives you a little bit better results, but eventually the main performance differentiator really comes from this idea of LDT entry caching, and that's actually where it comes from. That's where the power of the approach comes from. So we are trying to compare 3 cases. One is GCC that doesn't have any array bound checking at all, right? And the other thing is cache, that's ours. And the third thing is bound checking compiler. That's like the state-of-the-art software-based bound checking compiler. So these are 3 cases: no check, state-of-the-art software-based bound checking compiler, and cache, which exploits segment limit check hardware. So that we try sort of simple program, kernel program, loops with a lot of loops, and numerical programs and so on. So you have a set of program with SVD, volume rendering, 2D FFT, and so on. So cache incurs this kind of overhead. It's like 1.8%, 3.3%, and so on. So the original program run 100 milliseconds. This is going to run 101.8 milliseconds. This kind of thing. And BCC incurs, as we expected, 120%, 126%, and so on, right? Remember, the BCC also doesn't use that spread tree. That's why it doesn't suffer as much performance overhead as Imperial College bounce checking compiler. So this actually shows pretty promising. It is pretty promising, right? The overhead is almost nothing in the statistical noise. And the reason that it's so good is because if you really check the number of checks that the cache compiler generates that requires software fallback check is 0 for all these programs. Right? So the software checks there's no need for software fallback check. Right? So those things that we need to worry about, like you probably don't have announced segment descriptors, you probably don't have announced segment registers, and for some weird cases you need to fall back to software array bound checks. They do not happen. And that's why the performance overhead is so low. So, but this is just a toy programs, right? Micro benchmark. So let's try a sort of slightly larger program. So these are all a bunch of libraries that are pretty substantial. Some, for gzip to PNG converter, it probably has 47,000 lines of code, and so on. For example, the last one. So we also try to measure something in terms of the number of loops in the source code that contain that use array references. And then out of those, how many of them actually use more than 3 arrays simultaneously? Those are the cases that we need to worry about. Those are the cases that eventually going to require software array bound checking as a fallback mechanism. So the right-hand side, the column actually gives you the numbers, all right? So this just give us an indication whether this is going to be a problem or not. And then we actually run the program and then try to compare the differences. So again, the performance results is slightly worse compared to the micro benchmark results, but it's still not too bad. So the worst case is QUAT, it's about 16% performance overhead. But compared to BCC, it's 238% performance overhead, right? So again, I like to claim that this is really nothing compared to if we can have a way to actually stop all buffer overflow attacks with a performance overhead of 16%, it's pretty reasonable price to pay, okay? But again, these are just macro benchmark. What about like real applications? So let's try really, complete network application like Q, Hopper, Apache, SendMail, this FTPD and Bind, name server, and so on. These are big program. Nobody can claim that this is a toy program, right? Let's try real thing. And again, we do the same thing, analyze the whole thing, and then we do two tests. One is on latency test, and one is on throughput test. And the other is on sort of like binary space overhead. So latency is the amount of time required for a request to be sent in and get a response back. So we send thousands of requests and trying to measure the penalty in terms of latency. And the other thing is throughput. Throughput is like within a unit of time, how much stuff get done, right? And there's actually a difference between the two because of pipelining, right? So we just want to know, in terms of these two performance metrics, whether cache actually performs well. And space overhead is an increase in binary size. So it's because you actually have to add additional stuff, especially for the library part. So the space overhead is slightly larger. But as long as it doesn't affect the performance, people probably don't care. So again, for all these results, we are talking about under 10%. The worst case is SendMail. And the reason SendMail performs worse is because that it indeed has some loops that use more than 3 objects. And therefore, some of the array references indeed need to use this software array bound check as a fallback. So there are actually a couple of the lessons that we learned in this particular process. Remember, so the basic idea is very simple. Right? When we explain this idea to others, others tend to say, of course, you should do that. I don't know why people don't do it, but that's the. But there are actually some caveats. Like before you actually embarking on this particular project, you have to worry about this, worry about that, to see eventually all these ideas can fit together and pan out. And it turns out that the experimental results actually demonstrate that the idea seems to work just fine. Like, you can say we are lucky and so on, but, the common program that we need to worry about just work reasonably well for our assumptions. So for example, more than 90% of the time, 4 segment registers are sufficient, okay? So you don't have to worry about, like, maybe you have a loop that actually uses 10 arrays or 10 buffers simultaneously. That's just not a common case, okay, fortunately. And on the average, how many segment descriptors that we need? Remember, we have about 8,000 of them. It turns out that there are plenty of, there are more than enough for most of the applications that we test, right? 10 segments for micro benchmark programs, 163 segments for macro benchmark programs, 292 segments for network applications, and so on. And we also evaluate that idea of LDD caching. It turns out that the hit rate is also pretty high. Again, it captures this idea of, local array using a function called by within a loop. So that scenario actually is not too bad. So almost half of the time, we don't really need to go into the kernel. We can just do the allocation and deallocation at the user space. So there's actually no problem there. Now, there are actually a couple of limitations and misconceptions when people hear about this idea. People tend to be sort of a somewhat standoff issue when they hear about segmentation hardware or segments in general. So for example, they worry about, when I use the segments, would it actually introduce fragmentation, right? That's the well-known problem with segmentation, right? That, the reason that people choose not to do segmentation is because, paging gives you, better results in terms of eliminating this external fragmentation. And this is a misconception, right? Here, we don't really use segment to do memory allocation. every memory allocation you are doing, malloc and everything, is still page-based. Think of it as like it's already page-based. All I'm adding is that I just artificially add a fragment layer on top of it, right? So one way to look at it is I just have a bunch of pages. But another way is I'm adding a segment, say, oh, by the way, this part of this page and this part of that page constitutes one segment, right? So I'm not touching anything about a Linux kernel in terms of memory allocation. They do exactly what they are supposed to do in the generic Linux. All we are doing is just add a layer so that the way I'm generating references, I can use that segment. And I'm leveraging that segment limit check to perform that implicit array bound check for me. So that's sort of a good thing. And the other thing is that cache doesn't require so-called alias analysis, right? We don't really need to do pointer analysis to do this to figure out. For those of you who don't know, alias analysis basically means that in a program, a single object can have multiple names. That's the notion of alias, multiple names, right? And you have to figure out that maybe that multiple name, how do you determine that these multiple names actually refer to the same object or not? That's called alias analysis. We don't really need that because the way we do this is we carry the information about a pointer with it, right? Either we go through this static shadow variable or fat pointer approach, or we use a spreadsheet to look it up dynamically. So there's no need for alias analysis. We don't really statically, there's no sophisticated analysis like alias analysis you need to do. So, and then there are issues about if we only take care of references within an array, within a loops, then what about those array and buffer references outside loops? It turns out that we can do this using software array bound check without any problems. And compatibility with the existing code base. Yes, the original version of cache does have this problem because we use a fat pointer and shadow variable. But the second version of cache solved this problem by using that shadow stack on the heap approach. And then this problem goes away. We can demonstrate that this thing can work with the old version of glibc or cache compiled glibc together. There's no problem there. The only weakness with this approach is right now we don't support typecasting pointers. Like, so you have an integer, and out of the blue you cast it into a pointer. I cannot help you with that. So you have to have a well-written program that you already declare some variable as a pointer variable right from the beginning. And at the wrong time, you suddenly cast it into something into a pointer. That's not something we cover right now, right? So there's some limitation there, but we claim that that's probably not much an issue in general. And there are also some security considerations that I want to mention. So in theory, right now the cache compiler performance is actually already a little bit sort of pessimistic. It could be even better. And the reason is that in theory, we only need to check write access to arrays. Why do I need to worry about read access? Because that's not overflow, right? So I only need to check the write access. So that potentially can reduce the overhead even further, right? And the other thing is that some people is saying that, oh, you maintain this free LDT entry in the user space. Wouldn't that cause a security problem, just like you cannot put LDT at the user space? And the issue here is that, yes, there could be some security problem, but the worst that can happen is that the attacker can use this, can leverage this to crash a process, but not corrupt the underlying operating system. Okay, so that's the trade-off we have to live with. That they can massage this free LDT entry list, but the worst thing that can happen when that kind of tampering happens is that the underlying that particular process might crash, but not the corruption of the underlying operating system. Finally, our sort of new cache modified LDT system call guarantees that there's no call gate that can be set up. So this is the reason why we cannot maintain LDT at the user space. So we make sure that it doesn't happen. Now, up to now, we are talking about mainly buffer overflow, right? So remember the big picture. The big picture is that for control hijacking attack, there's this three-step procedure. And the first step is overflowing or tampering with the address space of the victim application, right? And up until now, I just explained to you that how we can actually stop that from happening. If you give me an arbitrary C program, I can compile it in such a way that these guarantees will never happen. Arbitrary C program, right? On Linux right now, I don't have a version for Windows, but on Linux right now, guarantee that won't happen, right? But then people will say that, what about other ways? No, yes, buffer overflow is fine, get rid of that. What about other ways? Can we do something about the other approaches to tamper with the address space of the victim application? So one way is integer overflow. So basically exploit overflow or underflow from finite precision computer arithmetic or typecasting. Like you cast some lower precision, so higher precision number to lower precision number, or you intentionally overflow or underflow your finite precision numbers. So the potential damages is it can crash the application because you can turn a number that's pretty small, but when you wrap around, it becomes really big, and you use that as an argument to malloc, and malloc doesn't allow you, and therefore the process crashes. All right. Or you can use this to exceed the bound, the lower and upper bound. But the second problem can be caught by cache. It's only the first problem that could cause a problem. So in the worst case, still, for integer overflow now, you can only crash the application if your application get compiled with cache. No buffer overflow can happen because of the integer overflow. So integer overflow sometimes can be used to mount a buffer overflow attack. Cache can catch those attacks as well, right? So the worst case that can happen now for integer overflow is really crashing. Okay. But if you really want to stop that as well, it's possible to add code to do this overflow and underflow software check for tainted arithmetic operation. That means that anything that comes from the network packets and they try to do some sort of arithmetic, you should do a double checking to see whether it actually wrapped around or not. So that's what it means. If you want to do that, you can add additional code. Now, the other way that they can be used to tamper with the network application's address space is a format string, right? So the idea is that the user can actually input a format string or input something that's part of the format string used in a print family of functions. So the damage could be, it could cause the information leakage. It can read the entire memory address space, or it can update arbitrary memory location. So that's pretty bad, the second one. So essentially, you can update, return address, function pointer, all these things. So right now, there isn't that good a solution around. But presumably, one way to solve this problem is you can add additional checks to ensure that the format string doesn't contain all these weird specifiers when printf has only one argument. So that's usually the problem. All right. So you can actually presumably do something along this line to stop format string attack. So the overall goal of the project is to say that nobody can touch my address space. That's what we want to do. And we basically get rid of the buffer overflow sort of threat. So we just have to move on to integer overflow and format string so that nobody can touch my address space. And then I don't have to worry about what actually happens after. Now, as a side note, this segmentation hardware, just as a history, the segmentation hardware in x86 architecture comes from this, Intel 432 architecture, right? Capability-based, this and that. And there's actually a reason why they actually implement this, because, this Intel X432 actually try to support various kind of protection model used in Martix, right? But people in research community, academic in general, and in commercial world simply ignore segmentation hardware. There's actually a well-known question asked by John Hennessy and Patterson in their computer architecture book. Is it useful? Is segmentation hardware useful in terms of improving the internet security? And all the work on cache demonstrates that yes, it is useful. And not only we demonstrate that, there are other people that also demonstrate that segmentation hardware is actually our friend. Unfortunately, it just get ignored for a long time. PAX project uses segmentation hardware to make sure that either you can write to something or you can execute something. You cannot both write and execute. So that's the way it implements the no execute pages. And then we also do another project that try to exploit segmentation hardware to do very fast intro address space protection domain. And that may be very useful for safe Java native method invocation. Right? When you have Java, unfortunately, there's this little thing called native method interface that allows you to interface Java with C. And so all your type security of Java might get screwed because you have a C somewhere lying around in the same address space. So conclusion, I just want to tell you that there's such a thing called cache. And this is the world's fastest array bound check-in technology for C and C++ programs on x86 hardware. This is an accurate, technically accurate statement, right? And moreover, it guarantees no buffer overflow attack. So with this, if you have an x86 box, there's really no reason not to use it. Right? You just compile it, on Linux. There's no problem. You don't really have to worry about all these other junks that people are talking about. And it's reasonably low overhead, right? I already showed you even for big programs like Apache and SendMail, it's fine. And our original concern that we have, software fallback, the limited number of segment descriptor, segment register, turns out not to be a problem. It's a good news that it's not a problem. Now the bad news is that unfortunately, IA64 on Itanium and the 64-bit version of AMD, Itanium doesn't even support at all. IA64 and AMD's 64-bit version only support segmentation hardware in the backward compatibility mode, not in their native mode. Right? So that's the bad news. So right now, it really only works on IA32 or in the compatibility mode of IA64. So future work, we want to port cache to Java. Right now, it only works for C. Java presumably is a simpler case, because it doesn't have a lot of pointers. And we already solved the legacy code compatibility problem. One of the things that we are thinking about is that how do we do this using source-to-source cache transformation? The problem is that we don't have access to the compiler source code on the Windows platform, other than that, Linux-like, GCC-like a platform. So we don't want that. We just want something like Visual Studio. Right? That's the kind of thing that people use today on the Windows platform. So one idea is that can I implement this idea by taking users' source code and then transforming it somehow and then compile using Visual Studio. That would be nice. Right? So just having a source-to-source version of cache probably can solve this problem of not being able to access the source code of Windows compiler. And then the ultimate goal is to stop all sort of tampering attempts into the address space. So the whole package is available in this particular web page, so you're welcome to download it and try it out. And we are committed to fixing the bugs if you have some bugs to report. So if you have any questions, I'll be happy to answer them. Yes? The hash within what hash we are talking about?
I'm sorry, we're talking about the user space cache.
Yes.
You have a cache of previous decisions to allow the for loops, for example, to be bypassed as long as it's being checked?
No, not really. So that hash, which hash we are talking about? Actually, I'm not really sure. So there's actually a hash that allows you to find for memory reference, which is the corresponding object. And then from there, we have to retrieve the corresponding segment and load the corresponding segment descriptor into the segment register. So for every memory reference, it's always checked. There's no bypassing. So the hash is mainly to look up which object it is so that I can load the corresponding segment into my segment register.
My accent is Australian, so what can I say is cache?
Oh, cache, yes.
Sorry about that.
So that cache only allows you to bypass the manipulation of LDT. So LDT entry is still within there, so you don't touch it because you don't make system call. So essentially, let's say I have an array, right, and I'm going to put it in the LDT entry number 3, okay? But the right way to do it is that every time I use it, I allocate one entry, and every time I exit, I deallocate it. And if the pattern is that the same object, the same array within a function needs to be allocated and deallocated, I say that don't touch LDT. At the user level, I can check, oh, this is the same guy. So I don't even need to allocate or deallocate LDT. So that's the main issue. But this has nothing to do with the actual array bound checking. It's just about how do you allocate and deallocate LDT entries. But you're right, it turns out this is, if there's a major idea, that's it. That's the idea that we hit on. Without that, the performance is sort of pretty bad. Yes, that could be a problem. So, as I say, that this is really an artifact of having only 6 segment registers. So, we are trying to convince Intel that, please preserve the segment hardware feature, and by the way, increase the number of segment registers. It's really nothing, right? I mean, it's just a couple of registers. There's no need to be, economical about this, right? But you're right that, if you use more and more, then some of these segment registers might get used for some other purpose. So we end up having smaller number of segment registers to use. But one potential solution to this problem is that we actually have to move the segment register as a part of the function call routine. Like when you save the context, you need to save the segment register as well, and you have to keep track of them and so on. So that sort of complicates the code a little bit. Yes. Yes, so that's what we are talking about. One example is this ES, that the glibc. So we carefully checked whether these segment registers have been used or not, and then the only thing that we find out is this glibc's string manipulation function actually use them. So as I said, in typical Linux, there are only 4 segments. So code CS, DS, SS, and some other thing. All right. So these 4 segments do not exist simultaneously, right? So they don't really use that many segment registers. The only sort of significant application that we can think of that actually use segments is this Wine project. They actually use segments. But that in general is not really a problem for now. This is actually GPL, yes. So the kernel dependency is very small. The only thing we need is that fast system call to modify LDT. That's the only thing. If you don't want that, and you don't care about that, you don't really need that additional kernel support. Now, everything we talked about here is actually user level. I mean, I can allocate the segment register anywhere I want it when I compile my thing, right? So there's no need for any additional kernel support. So, So the general thing is that the kernel support is mainly for performance optimization. But if you don't really want it, you can suffer. You can live with a little bit higher performance overhead. You probably don't need that kernel support. And then it should be pretty easy to port it to some other Unix-like platforms. Yes. First come, first serve for the first 3 arrays. Yes, we don't actually do sort of register allocation algorithm, coloring, and spilling and so on. So we think we are considering that, and we say let's try the simple approach, and then we never actually goes back because it doesn't seem to be a problem.
All right.
Okay.
Thank you.
Thanks.